All right, let's get started. So last time we've been looking at benign overfitting. In linear regression. So we have linear functions, quadratic loss, we're making the assumption that the conditional expectation, so expectation of y given x, we write as f star x is x transpose theta star. Expectation of x is 0, the covariance is sigma, and we assume that our coordinate system is defined so that things are, so our covariance matrix is diagonal, and the eigenvalues are ordered. So lambda 1 is the largest, and excuse me. And we were considering gradient descent in this setting on the empirical risk with, we have our x, y. Let's suppose that rank of x is n. So gradient descent converges to the minimum norm interpolating solution, which is this argmin theta such that we satisfy the normal equations, which is the, in the rank n case, we can write it as x transpose x transpose to the minus 1 y. Okay, and we were considering looking at theta hat in two subspaces. So thinking about our prediction with theta hat as, what we get from the first k together with what we get from the rest. Okay, so this is just fixing a k and considering what happens in these two subspaces, what happens with these two components of our prediction rule. Turns out that's the right way to view things. We'll see that later. But we saw that if we were lucky enough to have XX transpose to have the tail part of XS transpose, the low variance part, a scaled identity, then everything looked nice in terms of the kind of predictions that we got. So we were looking at that kind of property. When do we get some well-conditioned matrix of those inner products in the tail? So we saw this result at the end last time. There exists a constant, universal constant C, so that, we're thinking about the case where when we rescale our x's to make them unit variance, so if those components are independent for z with independent sub-Gaussian components. So think Gaussian, I guess independent, let's say one sub-Gaussian component. Then with high probability, N over C, we get this this result that, you know, 1 over, so the eigenvalues are, actually let's just write for an arbitrary matrix. So we get the minimum for our XX transpose eigenvalues are close to the expectation, you know, with a constant factor, C sum over I, lambda I, with these extra terms, you know, plus C lambda 1 N minus C lambda 1 N. And this implied that if that there are constant universal constants B and C, so that if the effective rank, which is the ratio of the eigenvalues, sum of the eigenvalues beyond K to the largest eigenvalue beyond K, is at least a constant times N, then these pieces disappear and we get, you know, we can replace this by a gamma, or a constant times gamma, lambda min of, and now I'll write this as x greater than k transpose, and lambda max is no more than c times gamma, with gamma these big eigenvalues, the sum of the big eigenvalues. That's right. That's right, yeah, I'm just, I was too lazy to put greater than k here, so we're working from k equals 0 up here. This is true for, under this assumption on the data in particular, also true if we look at the greater than k coordinates. And in that case, we get this effective rank for the greater than k things implies the same thing for this matrix, not the full Gram matrix.
Oh, but lambda 1 is lambda maximum.
Lambda 1 is the largest, yeah. Yeah? They're ordered. Okay, so let's have a look at why this is true. We'll do a proof. We'll be a little bit sketchy. Let's think about what happens in a particular direction. So we want to constrain the eigenvalues for a single unit vector. So for V, so for a fixed V with unit norm. When we take, so you know, we're defining this thing as the normalized version. So when we look at this thing, V transpose X transpose V, this is just the sum of the lambda i's times, I guess I wrote V transpose Zi squared. So that's, this is our sub-Gaussian random variable, and we're just looking in this direction V. This is a sub-exponential random variable, and so we get a bound on how this deviates from its expectation, which is the sum of the lambda i's. So, that thing, xx transpose v, minus the expectation of that thing is no more than, let's say, constants times the sum of the lambda I squareds times some t, square root of that, plus lambda 1 times t, and this is true with probability 1 minus 2 e to the minus t. We get something that looks like this, right, up to constants. So that's for a single direction. We can consider an epsilon net for some constant epsilon covering the sphere, right? For constant epsilon, the size of that net is going to be a constant to the power n, right? So we're in the n sphere here. This is an n by n matrix. So when we take a union bound over our epsilon net, that's a union bound over maybe epsilon is a quarter, right? Union bound over the something like a tenth or something to the power, 1 over a tenth to the power n. So, the union bound, this thing appears inside a logarithm over here. We get just scale that up. So with probability, at least something like, let's say e to the minus t. For all v in our epsilon net, this deviation is no more than something like a constant times, and we just blow up our t by log of the size of the epsilon net, plus lambda 1 t plus n. And then, this thing is lambda 1 times the sum. Let's do it the other way. This is the sum of the lambda i's times lambda 1 t plus n. So no more than that. All right, this is the biggest of those eigenvalues. And I guess I could write it as 1 over a constant times a constant. And then we have, geometric average. We can bound by an arithmetic average and get, this thing is small compared to that. So, the whole thing is, at least on our epsilon net, this is close to within this constant times lambda 1 of the expectation here. Okay, so this gives us our bound on these eigenvalues, that they're all tightly concentrated around the expectation here, the trace, modulo this constant factor, which means, in particular, when this piece is small compared to this one, then we get some absolute constant as our upper bound on the condition number of that matrix with high probability. Okay, so this is using all this independence, right? We're using the independence of the components here. In fact, we don't need to. We don't need this sort of property. We can get by with something that's much more a much weaker assumption. in fact, you can show, and maybe I'll put it down here, for if the X is sub-Gaussian, all right, so satisfies the sub-Gaussian inequality in every direction, then the condition number, I'll write it this way, the condition number of this matrix X, I'm going to use this matrix, X greater than K, X greater than K transpose, is bounded by a constant. So, with high probability, the condition number is bounded by a constant. In the sub-Gaussian case, this is equivalent to our effective rank condition, Rk sigma, being no more than a constant times n, and a small ball condition. With high probability, these components, the x greater than k vector, has a norm that's not too much smaller than its expectation. Let's put it this way. All right, and you can see the precise statement, the with high probabilities here, change in the two directions of the implications. But, if what we're chasing is having a condition number that's nicely bounded, then this rank condition and a small ball condition that ensures we don't have the mass too concentrated. So, we don't need this independence of components. In the sub-Gaussian case, that's kind of precisely what we need. Okay, and there's a bit of an argument sketched in the notes as to why we need both of those conditions. Yeah. What is? This the condition number, right? So this is the ratio of lambda max to lambda min for this matrix. Yeah. Okay. Having these Gaussian tails is also not necessary. You can relax that. You can get generalizations to more heavy tail distributions. You get something similar. You want a sort of anti-concentration of the norm and some notion of effective rank, but the effective rank notion changes if you're in a heavy-tailed situation. At least I should say, you can get sufficient conditions that have very much this flavor, sufficient conditions for the condition number being not too big. Okay, but we'll be thinking about just the sub-Gaussian case. It's probably a good moment to pause. So, we're thinking about this sort of decomposition, and a key tool here is going to be this high probability bound on the condition number of the corresponding component of this Gram matrix, the component of this Gram matrix that corresponds to the kind of tail, the greater than K components. Okay, and the intuition that we saw yesterday was here's a piece that's very much like a classical estimate in linear regression. Here's a piece that's going to give us a perfect fit to the training data, and we want that to be innocuous, right? All right, so in thinking about what we see for a minimum norm interpolating estimate, let's think about those bias and variance terms that we saw yesterday. All right, we can. All right, let's introduce some notation. So so we've got our noisy data. That's y the vector y is our data matrix times this theta star plus some noise. Let's call it epsilon. That's a vector here. We have our minimum norm estimate, which is theta hat. I'm going to write it, let's just use this. I'm going to write it over here as theta hat of y. Right? So, this is a linear function of the response vector. Right? It's just this matrix times that guy. So we can write theta hat of y, that linear function, as combination of these two pieces, theta hat of x theta star plus theta hat of the noise. So when we write, this expectation, so averaging over that y variable of the excess loss, right, LF minus LF star, this is the, we saw this decomposition into the two pieces. Okay, so we'll say this in a moment, but just if we're interested in that expectation, then we can compute those two pieces. The bias squared piece is the expected squared difference between f star and the expectation of f hat, the expectation when we average over the y's. So this thing is the sigma norm of theta star minus the expectation of this linear thing is, when we average over the y's, is precisely this. All right, so this is this quantity is a random variable that depends on the data matrix X. There's this term and there's another term, which is the variance piece. So that's the expectation of the expectation when we average over the y's versus the actual y's, and of course that's just taking account of the noise piece. So this is, think of that as expectation over the noise vector of theta hat of this thing. Again, we have a sigma norm. So these are the two pieces that appear in this case, just using linearity of our minimum norm estimate. Okay, and now, theta hat has this specific form, x transpose x transpose to the minus 1 times this thing. So we get, we can just write that out as I for the theta star minus x times theta star sigma. And this one we've got to look at, so theta hat here is same thing, x transpose x transpose to the minus 1 times epsilon. And then we're looking at this quadratic form. So it's that thing with an epsilon and that thing transpose. So we get, epsilon transpose stuff. So when we view that as let's write that out, expectation epsilon transpose times x transpose to the minus 1 x. And then we have this quadratic form, and then x transpose transpose to the minus 1 epsilon. Noise here. So this is the trace of a big matrix thing, and we can use this cyclic property of traces. That's just the expectation of this epsilon transpose, which is sigma squared, let's say, the variance of this thing, the components of this thing. let's say, sigma squared, or maybe we have an upper bound on them of sigma squared, or we're really interested in an upper bound here. So this thing gives us sigma squared times the trace of what's left. And I've written it in a symmetric way here, so leaving it in this order. Right, so these are the two quantities that we're going to be working with. Okay, and that's taking an expectation over y and leaving x random. You know, instead of doing a decomposition like this where we've taken the expectation, you could imagine getting high probability bounds on this thing. I should have written this as f hat, our specific estimate. We could aim to get high probability bounds on the excess risk. And then, you know, same thing, but we have a quadratic with some cross terms. We can upper bound those by, you know, 2 times this plus 2 times that. And then get high probability bounds on these various components, and you know, they're concentrated, or at least this one. Easy to see that this is going to be concentrated when the noise is sub-Gaussian, and we get, you know, with high probability, this thing is no more than kind of a constant times sigma squared times log 1 over delta times this trace. So, you know, these are the right quantities to be thinking about in that situation as well. Okay. Okay, so let me state the result here. I'm going to put the theorem on this board. So now to get bounds on these terms, let me think. Where are we going to? Okay, maybe we'll use this board. So the theorem here, and this combines results from work with Long, Lugosi, Sigler from 2020. So Phil Long, Gabor Lugosi, and Alex Sigler, and a separate piece of work with Alex from Pete in 2023. Okay, so here we've got, let's state it in terms of the giving the condition number as upper bound on the condition number as a condition of the theorem. So for 0 and delta less than 1, if the probability that the condition number of this greater than k matrix, Gram matrix, is bounded by some constant L. So, all right, for L in delta, if this is bounded by that with high probability and we have our k is good enough to give us Rk sigma is at least a constant times, universal constant times n. And let's pick the smallest k and insist that that's small compared to n. Then I've missed a probability statement, you know, then with probability, with high probability, I'll be vague. The bias term over here is bounded by a two pieces that just split into the smaller than k and the greater than k. And this is a sigma to the minus 1 on the norm of the heavy piece times something involving the tail. Plus, and then the light piece, the tail, we get a sigma star greater than k with sigma greater than k squared, and a variance piece that looks like a constant times the less than k part gives us just k over n, and the other part gives us n over another notion of effective rank. And this RK sigma, instead of, so little RK sigma was the ratio of the L1 norm to the L infinity norm for the tail eigenvalues. This one is the ratio of the L1 norm squared to the L2 norm squared. And you can see we want that to be large compared to n, right? So we get four pieces. You know, the bias contributed by the heavy part, the bias contributed by the tail, and the variance pieces from these two parts. Okay, so let's think about that. You know, this RK expression, the little RK expression that says we want that effective rank to be big compared to sample size, right? Once we, and that K better be small compared to, K better be small compared to the sample size. We get a variance here, K over N, that looks like the classical thing we'd get if we were just estimating in K dimensions. And in fact, the bias that we see for the tail is as if we're ignoring what happens beyond that, right? This term is just, you know, what we would see if we always gave a zero estimate for the tail. And in fact, you know, that's what we'll see, that really we're looking at the quality of our theta hat as an estimator of zero out here in the tail part. So you know, that's what's going to give us small contributions from those different pieces. We want the approximation error from truncating at k to be small, so that the variance better be small out there. We want a nice low dimensional subspace where we're actually doing some estimation, and that corresponds to this k. Okay. Let's see. So there are also lower bounds that have exactly this form, right? So up to constants. So you can show in the case of Gaussian data for any theta star, if you consider randomly flipping the signs of that theta star, you know, to get a lower bound, we do some sort of randomization, some symmetrization. If you consider randomly flipping the signs of the components of theta star, then you get, you know, the expectation under that randomization of the bias is at least a constant times exactly these terms, and the variance is at least the min of these things and a constant. So, you know, we can't, unless we impose some extra assumptions on the probability distribution, this is the best we can hope for up to constants. Okay, I should pause there for questions. Yeah, go ahead.
In the estimation of the bias, isn't there a square?
There is. Good, thank you. That's right. Was that your question, Konstantinos? No?
How do you see here the decrease in the loss function with respect to the number of parameters?
I'm sorry, how do we see?
Yeah, if we increase the number of parameters here, essentially we increase k, right?
No, we should expect to decrease k, right? Because Rk sigma is the effective rank of the tail. So if we have, let's say, essentially uniform variance out there in the tail, if we increase the dimensionality, then we're just increasing the rank, the effective rank of that tail. So both of these are helped by being in a higher dimension. Here we certainly need the dimension to be large compared to n. And here, satisfying this inequality is going to be easier when we're in a higher dimension, right?
So essentially, the margin of a neural network will increase the number of parameters, and so we decrease the loss function. Is there a way to connect that to the linear regression case here?
So there are examples where we can. Examples means, for specific families of probability distributions, we can make similar statements in these nonlinear settings. But I don't know of an implication for the nonlinear setting that follows from this. I mean, in this case, as I say, there are matching lower bounds. We can characterize completely, what when we're going to have the excess risk small, because we know exactly what all of the terms look like. The nonlinear case, much more limited in what we understand. So I'll talk a little bit about that at the end of this lecture. Yeah.
I have a question. I'm kind of confused. So if we believe in these bounds, there's no reason to take the largest coefficients, the smallest coefficients of lambda non-zero. You would like to have sigma to just cut to 0 after k, don't you?
No, because if you cut to 0 after k, you're never going to satisfy this effective rank condition. This is.
Otherwise, this is infinity after k. If the lambda i's are 0 after k, then this rk is plus infinity. So k is.
It's not plus infinity. It's 0 over 0. So yeah, okay. How do you define that?
I don't know.
It's the L1 norm over the L infinity norm. So yeah.
And so, can you connect these bounds with this double descent phenomenon? Can you read?
Yeah. So in this setting, double descent is looking at what does the excess risk look like as a function of the dimension of the space. And let's suppose we have a sequence of lambdas, and we're just going to chop things off after some point, right? So we're adding more and more dimensions. I mean, there's no guarantee. Like the plots that you see there, there's no constraint on what variance you're introducing as you add another feature. But let's suppose that we did it in order like this and just added dimensions. Then you can see from these expressions, which are tight within constant factors, how the excess risk is going to behave. I guess one other difference, the double descent curves are just showing risk. So another piece of that is what's the optimum that you can do in that particular subspace that you're looking at, right? And looking at increasing subspaces, this is going to go down, all right? But certainly you can make, you can play games, right? If you wanted to add in a subspace with a certain variance from the knowledge that we have of how that affects the risk, the excess risk, I guess, and the risk depends on what the theta star looks like in this new dimension. But then you can play games and have not just double descent, outside the classical region where d is smaller than n. Once you get out beyond that, you can make this curve do anything you like. I mean, within there's sort of a Lipschitz constraint that's imposed by the fact that you're taking averages of things out there, but you can come up with examples to have triple descent and some completely crazy up down forever behavior. So double descent is a situation where you're adding in the dimensions and actually you do have a decrease in these things, and the approximation error is not improving too much. But we can calculate exactly what happens at every point on that curve. Up to constants, I guess I should say. Okay, so let's have a look at why we see this sort of how these upper bounds are proved. I'm actually just going to restrict to the variance upper bound. Let's think about that. Of course, we're splitting into those components, and we'll see how the components contribute to that bound. I want to split the proof into a kind of deterministic piece under the condition that we have our condition number small, and a probabilistic piece. So this is the approach taken in this paper, and we see that it really is. We do most of the work in looking at the kind of algebraic properties rather than linear algebraic properties, rather than making any probabilistic claims until the end. So that part is nice and simple, the probabilistic part. Okay, so when we do a split in this kind of a way into the smaller than k and greater than k pieces, we can think about our theta here as solving an optimization problem. But if we split it into two pieces, then you could view, what's the value of one of those pieces as a function of the other, for instance. Okay, so we're going to do that. We're going to think about, define a problem. Okay, so let's say proof sketch for this piece. Let's define an optimization problem, which is the min over, so let's suppose, I'm going to give this the name minimum norm interpolant, I guess, MNI, let's say, theta hat less than or equal to k. So somebody's given us this, the first k components, and then we want to identify, what's the rest going to look like. We've got a theta greater than k. Well, we've got to minimize the norm of that, because the sum of the squares of the norms is exactly the thing we're minimizing, subject to the interpolation condition. Well, we've got this thing fixed, and now we're going to make sure that when we look in the greater than k directions, we get exactly y, but we already have the less than or equal to k guys giving us some contribution. Okay, so this is an optimization problem. If you tell me what you want the heavy parameter pieces to look like, then this is what the tail pieces will look like. Okay, and we know how to solve this problem. It's just a minimum norm interpolation problem with this. We're wanting to get that interpolant, so the solution is just, I'll write it as theta hat greater than k. And it's this thing. and we need to know that we can invert that, but we're in a situation where the condition number is nice. So in particular, all the eigenvalues are within constant factors of each other. So it's positive. In particular, they're positive. And this is the thing we're interpolating up here, less than or equal to k, theta hat less than or equal to k, and I forgot the hat up here. Right? This is a parameter of the optimization problem. Okay, so now so now we can express everything just in terms of the less than or equal to k guy. All right, so we can define a mapping that if we're looking over this k-dimensional space where our theta hat less than or equal to k lies, then the solution to this optimization problem is going to look like, if the theta hat less than or equal to k takes a particular value, then that's the component we see for the first k, and for the rest we're going to see x greater than k transpose blah blah blah. Right, so this whole thing is an affine map from Rk to what are we in, Rp, and to get the solution to, so that's if we've fixed a theta hat less than or equal to k, to get the solution to this optimization problem, we want to have that thing of minimum norm. All right, so we've got this picture that, here's our subspace, our k-dimensional subspace that corresponds to the image of Rk through phi. So, for some point here on this subspace, we have like a, phi of some theta hat less than or equal to k. We're interested in the minimum norm one. So if this is the origin, we're interested in this guy. I guess I should have written, let's write theta hat as the optimum. So if we get the solution to our optimization problem out here, and this is some other one, right, that's some other point, then the minimum norm one, satisfies these normal equations, that when we perturb things in this direction, we have to be orthogonal to that direction. So, go and calculate what that means for this affine map, and you get an expression that, this thing, let's see, the inner product between this minus that and this has to be 0 for all eta in Rk, which means we can write that we can write a the first piece of that inner product looks like this. The second piece is this when we're moving in the eta direction, so we lose the y piece when we consider that difference. So we get okay. This is the second component of phi, which has the y piece, theta less than or equal to k, transpose the inverse x, and that's greater than k transpose inverse, and then we have the difference between this and this plus eta, which gives us another one of these, and this, and then it's just this times eta is the difference. So we lose x greater than k transpose times x greater than k transpose inverse, and we keep one more less than or equal to k and eta. All right, so we have an expression that looks like this as that inner product. So our normal equations are, we want to be here, and that's for all eta. And so, you can write things down as, this vector that's orthogonal to eta for all eta must satisfy this expression, right? Plus x less than or equal to k. I'm flipping a transpose around. Times this thing, which is an x less than or equal to k, times theta less than or equal to k, and then there's a y piece. I'm going to write the y piece on the other side, that this thing has to be equal to this expression. Okay, which is the constraint that the solution to the min-norm interpolation problem needs to satisfy. And now we can just think about the in this case the variance piece, which all right, I want to write it as variance is the piece that looks at theta hat as a function of, when we think about just seeing epsilon as our responses, seeing the noise as our responses, and it's the expectation of this over epsilon. We saw, we wrote an expression for that, but I'm going to write it out as the two pieces. There's the less than k piece, so this is less than k piece as a function of epsilon, of the noise, plus the other bit. Okay, so let's think about what happens with those two pieces. First up, for this guy we get, I'm going to write maybe over here. All right, so we'll use the optimality condition to prove an upper bound on the norm, an upper bound on this quantity. So we're going to start with taking this thing times epsilon. So what am I doing here? I'm gonna say that quantity is no more than the norm of this, because that's what I want to get control of. Theta less than or equal to k epsilon. I'm going to write a sigma norm. I guess it's sigma less than or equal to k. Times the other piece, which is this vector epsilon with a sigma inverse norm through Cauchy-Schwarz. And now I can look at what happens for this kind of quadratic form involving theta hat and epsilon using our expression here for the constraint that the first k components need to satisfy. So this gives us that's at least this much. We can write that out as theta hat k epsilon. Here, that thing, what can we write? The inner product between that and x, and so we're putting epsilon in for y. That's this thing on the right here, and considering how it lines up with theta hat, the corresponding theta hat k. So on the left we get a theta hat k, more than k, epsilon norm squared. And then the other piece is a kind of quadratic form involving theta hat less than or equal to k epsilon. So we get x less than or equal to k transpose this thing. Okay, and now, this is certainly bigger than 0. We'll ignore that. It's not the norm that we want. And we can lower bound this because we have, this is something that we've got control of its eigenvalues. So we're going to be using that. So it's at least as big as the minimum eigenvalue of that matrix, that piece of the Gram matrix. And then this other term in our quadratic form. What's left? And now, we can be a little bit. We're gonna write this whole thing is at least the minimum eigenvalue of something involving a nicely normalized sample covariance matrix. So I'm going to write this as the lambda min of a matrix in the middle where I put some sigmas in here to appropriately normalize things. So I'm going to say this to the minus a half times x less than or equal to k transpose times x less than or equal to k times sigma to the minus a half less than or equal to k. We're taking the minimum eigenvalue of that, and we now have a sigma to the half on either side. Well, that's just this thing. Epsilon sigma less than or equal to k. Okay, so we've got this thing compared to that thing squared. We get an upper bound on the sigma less than or equal to k norm, which is what we want to bound. We get things as a ratio of this quantity, or at least the expectation under sigma of that quantity divided by this quantity, and I guess we need to square all of those to give us an upper bound on this thing. So let's write that over here, that we get something that looks like an expectation over the epsilon of this term less than or equal to k transpose. This is the inverse. That's just a sigma, an epsilon. And we get some norm here that's the less than or equal to k to the minus 1 norm. We want an expectation of that over the other terms. Okay, so when we take, and we're going to be squaring things and computing an expectation, when we take our, go ahead and compute that expectation of this thing over, various other terms, this ends up looking like the variance of the noise. We can bound it by the maximum eigenvalue of this matrix in the middle that we know is going to be well conditioned. And a trace of something involving these guys and that matrix, right? So this is trace of x less than or equal to k, sigma less than or equal to k to the minus 1, blah, blah, blah. On the top line and on the bottom line, we get just these minimum eigenvalues that we were playing with here. Lambda min times the other one. Blah, blah, blah. That's for the less than or equal to k piece. And I should write, plus something. And I've run out of space to put the other piece. And then we can go ahead and do the same thing for the greater than k components. Again, that one is much more direct. We're just directly bounding what we see over here. It was that sigma squared trace term that we saw earlier, and that gives us another term proportional to sigma squared with a lambda max and a trace that's very much the same sort of flavor as one of these. So I'm going to write out the conclusion that we get from those two pieces, that the variance term, as we go through and use this, so we get the variance term is no more than this ratio of the max eigenvalue of our tail gram matrix times a trace x less than or equal to k times a sigma to the minus 1 on this lambda min of that times a lambda min of, and now we have the less than or equal to k piece okay, and now I'm going to use up the whole board. The second piece is just the calculation of an upper bound on this that involves that trace expression we saw that had the product of a bunch of those terms, which just looks like a sigma squared times lambda max of the terms that were in the lambda max of this thing that we see everywhere. Times the thing that's in the middle here, which has the x transpose for these tail guys. With a transpose in the right place. And they're the two terms in our upper bound on variance. So now let's think about what those terms look like in our setting. So first of all, okay, so this is really just an algebraic argument. We're really just saying, look, when we solve this optimization problem, the theta hat less than or equal to k and theta hat greater than k have to satisfy this affine constraint that relates them. That affine constraint lets us get a handle on the way the scale of theta hat less than or equal to k epsilon, the way that the scale of that behaves. And then, and the other piece is just a sort of easy approximation, that second piece. The piece that corresponded, I guess, to making sure that we don't have a very high variance in that tail when we were looking at that. Imagining that example where this matrix actually was a scaled identity. Okay, so they're the two pieces, and now we can think about what the nature of these random variables tells us about the various pieces. Okay, so let's look first of all at this trace. Okay, these are x's scaled by sigma to the minus a half, right? So they're normalized. So here we're looking at, the trace is the sum of the diagonal entries, which are just independent and identically distributed, and they have this variance 1. So we're just getting something that's tightly concentrated here around k times n. All right, k terms, each one is a sum of n things, n IOD things. What else do we have? When we look at, I guess there's another very similar here, right? This is the same when we're looking at the tail. Again, IOD diagonal elements that have been normalized. In this case, the variance, I'm sorry, they haven't been normalized. So in this case, we have a variance to sum up. So these things are tightly concentrated around their expectation, which is just n times the sum of the components. So I greater than k of lambda I for that piece. What else do we have? This thing down here, that's a sample covariance matrix, right? But it's a special one because we've normalized the XX transposes that we're summing here. It's a scaled sample covariance matrix with n isotropic vectors in Rk. So provided that k is much smaller than n, that thing is going to look like n squared. I guess I missed a square somewhere. This should look like n, and this is lambda min of that thing squared. To give us an n squared. And then, what else do we have? Okay, so these things, did I miss a square for them too? I did. These are lambda min and lambda max of the squares of those things, and I think I'm right with this one. So we have this thing well conditioned, under the assumption of the theorem. So this is just a constant ratio, and I guess we have to take account of the scale of that thing on this side, and that looks like it's squared. This is the sum of the eigenvalues. Greater than k. The sum of the tail eigenvalues which was, so when we computed this condition number, you know, we just need to know the expectation to know what it's tightly concentrated around, since to know what the lambdas are tightly concentrated around. And so we have, you know, this is just the sum of the lambda i's, but we're taking it to this power, right? Within a constant of this thing. Okay, so, you know, put all that together and we get, this goes away, it's sigma squared k over n for the first term. Second term is sigma squared times n times this thing divided by that thing squared, which is missing, what am I missing? I'm missing a square, right? So this is a trace of the sum of the lambda I squared, because, yeah, so I had a lambda I from here, and I have a lambda I from there. So I've forgotten I got the exponent wrong there. So, you know, this is where this other term comes from, n divided by, so n times this divided by that. How are we doing? Okay. All right, so that's where at least the variance term comes from. Bias term, we're using the same affine relationship. Actually, you can go. It's not yet in the notes, but there's a related calculation to estimate the bias term. As I say, these estimates are tight within a constant factor unless you have some extra information about the probability distribution. So there's a Gaussian, the Gaussian case shows that.
The constant term on the variance is the true variance of the node.
I'm sorry?
The constant term.
Oh yeah, I've missed a sigma squared. Thank you. Yeah, this all has, because I think in the notes I wrote V for variance over sigma squared. So yes, absolutely, this term scales with sigma squared as I wrote it there. Any other questions? Okay, so you can see, you know, we do this decomposition. We have this kind of characterization of when you'll get a nicely conditioned tail piece of that Gram matrix, and that's kind of exactly the right thing in this setting, right? Gives us control of these four terms. Okay, so you know, there's a bit more talky talk in the notes. I guess I wanted to say we saw the other day when we imagined that this matrix was a scaled identity, we saw something that looked a lot like ridge regression in the in the k-dimensional subspace, the heavy subspace. And actually, we can come up with that. We can get a little more insight into that that relationship by rearranging the form of these four terms. So, so here, if we look at right, so let's consider the kind of equivalent regularization coefficient was the largest, smallest, all the eigenvalues of that matrix, the x greater than k, x greater than k transpose matrix. So let's define gamma as this quantity, the I greater than k, sum over I greater than k lambda I. We know that the eigenvalues are within a constant factor of this. I'm going to scale it in a way that reflects, our choice for k. We choose k as the smallest one for which b times n is smaller than the ratio of this to lambda k plus 1. Right? So define this, then the k equal to the minimum value over here of k prime, such that this effective rank at k prime is at least b times n. That k satisfies this condition on the eigenvalues. Lambda k is at least, gamma is at least lambda k plus 1. Right, because gamma being bigger than lambda k plus 1 is equivalent to this condition, right? And it's the first k for which that's true, so it wasn't true down here, and it suddenly is true up here. Okay, so we get this comparison between a scaled version of our regularization coefficient and the eigenvalues. And then we can go ahead and rewrite these expressions. So let's erase. Rewrite these expressions in terms of gamma and all the eigenvalues. And we get something that looks just like a ridge regression kind of result, right? So we get that the bias term, we can write it as something like the first term here is the sum over the guys that are smaller than k of theta I squared over lambda I. That's that norm, but now we have a sum of lambda I squared over n, sum of lambda I over n all squared, which is gamma squared with a b in there. Let's drop the b and incorporate that into our constant. So right, this kind of a thing. Plus the bigger than k part is just a sum over I of theta I star squared times lambda I. And that thing's equal to, because we have this relationship between gamma and lambda, I can write that as theta I squared divided by the max of 1 and lambda I over gamma squared. Funny way of writing, because we know that gamma for the I up to k, lambda I is bigger than gamma. So we're just getting this term, right, which is not right. What am I doing? I've got a theta I, I've missed a term, theta I star squared, lambda I squared over lambda I. Right, so I can write things this way for the first one, and why did I take the max? Because I can write exactly the same thing over here, right? Right, and in that case, we're greater than k, and so all of those eigenvalues are smaller than lambda, and we just get this, the 1 there. And these are within constants of, the usual way of writing this. This sort of expression is in terms of a lambda I divided by 1 plus lambda I over gamma. And we don't need to restrict our, so you know, modulo a factor of 2 somewhere we have exactly that. Okay, and similarly you can go through the same argument and write the variance terms as no bigger than the sum over all I of lambda I over gamma plus lambda I squared. And that's a 1 over n. Okay, and you know, if you're familiar with what happens in fixed design ridge regression, this is exactly what the bias and variance terms look like there, where these lambda i's are the eigenvalues of the design matrix covariance. And in that setting, you know, people call this quantity the effective dimension, right? This is where gamma is the regularization coefficient for that ridge regression estimate. So, you know, this should be a familiar expression for those of you that have seen that, and if you haven't, it's in the notes, even with a short proof. Okay, let me pause for questions, and then we'll look at any.
Fuzzy question.
Yeah.
Do you have beyond algebra? Do you have any interpretation of those two effective ranks, the little r?
An interpretation. Yeah.
I don't know. It looks like the little r is like giving you. If you wanted to select an actual k, it depends on the little r. And
Yep.
the big R is something else. I don't know if you have any intuition on that, or
Yeah. So there is a lemma in the notes that gives a bit of a story about these guys. The little r is always smaller than the big R. They can't be too far apart. There's like a factor of n. I'm sorry. There's a lower bound that's you know, the square. One's bounded in terms of the square of the other, and I've forgotten the expression that big R is no more than little r squared. So, you know, they're related notions of effective rank that, you know, for excess risk to be small, both need to be large compared to n. The kind of most favorable situation is that there's a k where the effective rank suddenly blows up to something that's way bigger than n, right? And at that point you have, you know, the nicest behavior because you've got these excess risk terms, you know, that at that right value of k, you have these excess risk terms that are you know, nice and small. So yeah, I mean, I think in terms of intuition for these effective ranks, it's good to think about, you know, a finite matrix. So all of this story is true, I guess, in Hilbert space, right? There's nothing about P that we're caring about here. You know, if you think about a finite, think about the sigma here being a scaled identity, you know, then these things are exactly the rank. If it's not a scaled identity, if the eigenvalues are actually dropping, then it's kind of the rank times some notion of sort of symmetry of those eigenvalues. If they're all the same, you know, this scaled identity case, it's exactly the rank. If they're more asymmetric, then it could be, you know, something that's much smaller, right, than the rank. But it kind of fits in between those extremes. You know, it's up to the rank of the tail. So it's clear we really need to be in high dimensions. You know, that's required. But even in high dimensions, if those eigenvalues are dropping too rapidly, you know, that's bad news. In the infinite dimensional case, you can play around with these things. If you have kind of a certain rate of decrease of the eigenvalues, you can see what that implies about excess risk. And the kind of in infinite dimensions, it's sort of hard to have the excess risk going to 0 as the sample size grows. You know, you can have an appropriate rate of decrease, but it needs to be sort of almost not summable, right? The lambda i's need to be right on the edge of being, you know, having a convergent sum. In the finite dimensional case, it's a much more generic situation. So if you have very high dimension, but you truncate that dimension at some value, and work with, you know, some pretty slow rate of decrease of eigenvalues, sufficiently slow, let's say, but you've truncated it, then you'll get the asymptotics that this thing is going to 0. So it's sort of high dimension, slowly decaying eigenvalues, truncated at some finite but suitably growing dimension. I mean, we need to have the rank, you know, the dimension big compared to n. So as long as it's nice and big, then you know that case where you make it high dimensional but truncated, finite dimensional, is exactly the sort of, you know, generically you see this condition then. Yeah. So yeah, but you're asking, I guess, about the intuition of the. Yeah. Yeah. I mean, you know, if you think about, I think the most natural intuition is writing things. I put this in the notes. You know, you can write the rank Rk of sigma as the rank times. You know, there's this sort of symmetry function, Sk of sigma, which is something that lies between 1 over p and 1. And it's, you know, I'm just rearranging symbols here, but it's this quantity, you know, the average of the eigenvalues divided by that, I guess, I greater than k divided by that k plus 1. Right? So this is some notion of kind of how lambda k plus 1 compares to the average of everybody out there in the tail. And you can write a similar expression in terms of the large capital Rk. All right, so it is incorporating that kind of how symmetric are the eigenvalues from that point on. All right. I wanted to say a little bit about open problems. Maybe give me 30 seconds to go over time on that. You know, just in the benign overfitting setting, we talked about regression here, the classification case. We know a lot about it in the case where we're considering the minimum norm interpolating solution. So where, for instance, you work with, let's say, a quadratic loss, and you're considering the minimum norm case. You know, when you think about things like the large margin solution that we saw emerged with logistic regression, you know, much less known there. Does seem to be so much less known. We know about examples. You know, you can come up with sufficient conditions on probability distributions for which this sort of benign overfitting phenomenon appears in the classification setting. But you know, here we get kind of a characterization, right? The covariance matrix looks like this. That determines exactly the excess risk. We don't have anything of that sort of generality in the classification setting. You know, when we want to move to your question, Konstantinos, when we want to move to nonlinear models, you know, what happens? What's the corresponding decomposition look like? Again, we have specific examples of probability distributions, classes of distributions that suffice to get this kind of thing happening. There it's more complicated because you have to worry about the optimization side as well, right? You want to know, you know, that you get to a suitable solution and the properties of that solution. You know, I think there are a bunch of interesting directions that are suggested by the fact that, you know, everything's going on in a simple subspace here with a small subspace. You know, does that mean that there's at least in nonlinear settings, that there's some sort of ability to distill a simple model and work with that instead of being massively over-parameterized with all of the costs associated with that? So I think that's a really interesting direction. And of course, in the linear case, there's no advantage to doing this if you're doing linear regression, right? You don't want to have an overfitting solution. We know about what to do in that case with efficient algorithms. But of course, in the nonlinear case, it does seem that there's this, at least empirically, it seems that it makes this global optimization tractable going into the highly overparameterized setting. And of course, that's, I think, really a really interesting direction. Why is there a computational benefit, or when is there a computational benefit to chasing these sort of overfit solutions? So, a bunch of directions. There's really a lot that we don't know, and I think the cases we know about have the status of pretty simple examples. So, I think it's kind of exciting from that perspective. Okay, and let me finish by saying a big thank you to the organizers, Haseen and Boris. It's been fabulous. I've really enjoyed coming to San Flor. My first time also. So yeah, thank you very much. Fabulous. And thanks to all of you as well. It's it's been a pleasure giving these talks. I appreciate it.